Sleep research has a persistent blind spot. There is no physiological marker to definitively prove a person is actively experiencing a dream. Without a real-time monitor for dream content, neuroscientists are forced to rely entirely on retrospective verbal reports given by subjects after they wake up. This reliance on waking memory introduces massive subjective variables. It creates a chasm between the actual biological event occurring during sleep and the narrative the subject pieces together later. Historically, researchers had to bypass this gap by observing patients with severe brain injuries who reported a sudden, total cessation of dreaming. Today, sleep labs rely heavily on electroencephalography, or EEG, a test that detects electrical activity in your brain using small discs attached to your scalp. But while it maps voltage fluctuations, it fails to capture a single frame of the actual imagery or content of the dream. When subjects are awakened from rapid eye movement, or REM sleep, they yield dream reports up to 95% of the time. Awakenings from non-REM, or NREM sleep, the slower wave periods lacking rapid eye movements, yield significantly lower recall rates. The reports that do emerge share distinct cognitive characteristics. They are highly visual, multimodal experiences structured as a continuous narrative, lacking in self-reflection or metacognition. Because recall rates fluctuate so wildly depending on the specific sleep stage at the time of awakening, researchers traditionally categorize dream recall merely as a fragile, state-based memory phenomenon. This methodology trapped the field in a corner. For decades, scientists were studying the fleeting state of waking memory rather than investigating the hardwired, sleeping structure of the brain itself. To understand the chemical fragility of these memories, consider the standard morning alarm clock. A sudden, jarring awakening triggers an immediate spike in norepinephrine levels. This stress hormone instantly blocks the specific neurochemical pathways required to hold on to the dream narrative. To bypass these daily chemical spikes, a team of researchers in France isolated two extreme cohorts based on long-term habitual behavior, rather than the results of a single night in a lab. The first group was classified as high dream recallers, or HR. These individuals naturally report remembering a dream more than 3 days per week. The second group, low dream recallers, or LR, report remembering a dream at most twice a month. Over months and years, these two groups maintain this stark difference in recall frequency, regardless of their daily waking habits, the alarms they use, or sleep stages they wake from. If high recallers and low recallers maintain this vast gap, despite experiencing the exact same chemical states of waking, the variance must be hardwired into their anatomy. To prove dream recall is a permanent structural trait, researchers needed to locate the exact anatomical difference between the physical brains of these two groups. The most intuitive neuroanatomical assumption, held by both the public and early researchers, is that people who remember dreams must simply have denser, stronger primary memory centers. Specifically, this assumption points to two deep brain regions, the hippocampus, which is responsible for episodic memory, and the amygdala, which handles emotional processing. To test this, scientists used voxel-based morphometry, or VBM, a high-resolution MRI technique comparing brain anatomy down to individual millimeter-sized pixels. Before analysis, the raw brain images undergo rigorous pre-processing. They are normalized to a standard stereotactic space, corrected for magnetic field bias, and mathematically smoothed to allow for precise one-to-one anatomical comparisons across all subjects. VBM makes a critical distinction between two types of tissue. Gray matter consists of the cell bodies where actual neural processing occurs, while white matter is made up of the myelinated axonal tracts that act as cables connecting those regions together. When researchers ran VBM scans on the amygdala and hippocampus, the results returned a statistically significant null result. Because there's zero structural difference in these memory centers between cohorts, dream recall frequency cannot be explained by hippocampal or amygdala density. While the density of the hippocampus and amygdala does correlate with the bizarreness or emotional load of a specific dream, it does absolutely nothing to dictate the frequency of recall. Forgetting a dream is not a failure of anatomical memory storage. The capacity to remember is dictated by a completely different neural architecture. With the temporal lobe ruled out, the researchers shifted their anatomical focus to the front of the brain, the prefrontal cortex. Here, the neuroimaging data revealed a massive, isolated structural variance between the two cohorts, located precisely in the medial prefrontal cortex, or MPFC. High dream recallers possess a significant increase in MPFC white matter density. This 172 voxel anomaly is pinned to specific MNI coordinates. The bar plot highlights the clear parameter estimate gap between the high recaller cohort in red and low recallers in gray. It is crucial to note that the VBM scans found absolutely no gray matter density differences across the entire brain. Because the variance exists exclusively in white matter, high dream recall is a function of structural connectivity rather than localized processing power. This new scanning data perfectly aligns with decades of historical neuropsychological lesion studies. Researchers found that physical lesions in the white matter surrounding the frontal horns of the MPFC result in a global or partial cessation of dreaming. These specific lesion patients stop reporting dreams entirely, yet they do not experience any other concurrent sleep disturbances. The data paints a clear picture. The MPFC white matter acts as the generator for dreaming. Its structural integrity is required to produce the dream in the first place. We can trace the physical connective pathway of this specific MPFC white matter downward, deep into the older structures of the brain. This continuous anatomical tract is known as the mesocortical mesolimbic dopamine system. Current neurological theory suggests that this dopamine-rich circuit acts as the primary generative engine for the dream narrative. The increased white matter density found in high recallers means they physically possess a thicker, more robust connection along this specific dopamine circuit. Low recallers, by contrast, have thinner white matter tracts, representing a lower bandwidth connection between frontal logic and limbic emotion during sleep. Remembering a dream requires a highly efficient, high-bandwidth physical cable connecting the brain's reward centers to its prefrontal projection screens. To understand what this extra white matter bandwidth actually processes when we aren't asleep, we have to look at the MPFC's role during waking hours. During the day, the MPFC handles social cognition, interpreting the minds of others, and projective imagery, the cognitive ability to envision the self in the past or the future. These functions are tied to the default mode network, or DMN. The DMN is the synchronized brain system that takes over when we are at rest and focusing entirely on internal thoughts. The MPFC serves as the central frontal node of this mind-wandering network, orchestrating those internally oriented mental processes. Positron emission tomography, or PET. A PET scan is a functional imaging technique that measures metabolic activity in the brain. This scan data proves that the DMN does not shut down when we lose consciousness. It maintains tonic activity throughout NREM sleep and becomes highly active during REM sleep. Correspondingly, drops in MPFC activity align directly with sleep stages, like N3, that produce far fewer dream reports. This correlation integrates dreaming into the broader study of cognition. It is no longer considered a mysterious, isolated sleep phenomenon. A dream is simply an intensified, unconstrained form of the DMN's waking mind wandering, authored by the exact same regions we use to imagine our futures. When we combine the neuroimaging of white matter density, the function of the MPFC, and the activity of the default mode network, the biological reality of dreaming comes into focus. We do not remember our dreams simply because we happen to wake up at the right time or sleep a bit lighter. High recallers remember their dreams because their brains are physically, structurally wired with the bandwidth required to sustain the DMN's internal simulations through the chemical fog of sleep. The next frontier for this research is determining causality. Researchers must find out if this dense white matter is an innate genetic trait or an acquired physical adaptation built by actively paying attention to dreams over a lifetime. It is entirely possible that practices like keeping a daily dream diary might increase the physical density of these neural pathways over time through neuroplasticity. Dreaming is not a fleeting state of mind. For those who remember, it is a permanent architectural feature of the brain.